Hey, in this video we'll learn how to prepare the full bridge controlled rectifier in Simulink, as well as we are going to discuss the result. I'll also share some of the tips through which you can also speed up your simulation and analysis. So without wasting time, let's get started. So to prepare the circuit, we'll go to library, and in library we'll go to SimCaps. Here it is. In SimCaps we'll go to power system, and in that power system specialized technology, and in specialized technology the fundamental blocks. Here in the fundamental blocks, electrical sources, and we'll start with AC voltage source. We'll add it, then we'll add the load. We'll use RLC branch. Then we want some power electronics device, so we'll go to power electronics. Here we have varieties of device: idle switch, IGBT with diode, MOSFET, GTO, thyristor, and a ready-made full bridge converter, right? But we are going to use this thyristor. Full bridge rectifier is a simple circuit, and creating it by yourself, it gives you a detailed idea. So I suggest that whenever you are going to prepare a simple circuit, do not use ready-made bridge. Create it by yourself so that you can have in-depth idea. So here we have all the components. Just click Control and drag it. It will duplicate this device. Control plus R, it will rotate it by 90 degree. So power circuit is almost ready. Now we are going to provide the gate pulse. To provide the gate pulse, we are going to use the pulse generator. Double click it and write pulse generator. If you want to learn how to use pulse generator properly, then I have created a separate video. You can watch that video and learn how to use pulse generator in detail. Period would be 1/50, pulse width 5% enough, and phase delay would be A into 0.02 divided by 360. Now our entire circuit is ready. Gate pulse of switch S1 and S4 are same, and gate pulse of switch S3 and S2 are same. Why it is like this, I will explain it little later. Now exactly what are the results that we want to observe? Basically we are interested in observing the input supply voltage and the output voltage. So what we can do, just double click it and in measurements select voltage. Okay. In load, branch voltage, branch current, voltage and current. So these are the different parameters you can measure. Right now we are interested in only voltage, so we'll select branch voltage. Okay. Now we are going to set the supply parameter, the peak amplitude of the voltage. If you want to keep 220 volt RMS, around 320 volt would be the peak magnitude. Phase delay 0, frequency 50 Hz. That's it. So almost everything is ready. Now we are required to add the thing in which we can observe the output. So first we have measured the output, and now we are going to use multimeter. This is our multimeter. Using this multimeter, without any wire connection, we can get the signals from the source and load to this multimeter, and through this multimeter we'll see the signals in scope. So we require one scope. So we'll add one scope. If you want to quickly add the device, what you're supposed to do, just double click it. So this window will pop up, and here you need to write the name of the device. For example, I want to add scope, so I'll write scope, and there we go, we have the scope, right? So this is more quick and easy way to add the devices. But if you are beginner, may be possible that you do not remember the name of the devices. For that you need to go to the library browser, and in this sources and sync you can get all the important components, and if you don't know that, then you can search it from here. So now just double click this multimeter. The first error multimeter show is this. So we'll remove this error. This error is because here we have provided A plus 180 and A. So we have not defined the A, and that is why this error is popping up. One more error will come because we have not used one block. We have intentionally not kept that block in our system right now. So first let's add the value of A and then we'll proceed. So here, for example, we want to add A is equal to 60 degree, right? So our firing pulse would be at 60 degree. Now again it shows the error, and this time this is because we have not added the power GUI block. Why we require power GUI block? In depth, in detail video of the power GUI block, around 4 minutes of video I have created on the power GUI block, that why it is required, what is the need of power GUI block. I insist, if you are working with Simulink, you must watch that video. Right now here I am directly adding power GUI block. So here we go, we have this power GUI block. Now there we go, we have no error. So first we'll select this voltage source, we'll get it on right hand side, and then the R load close. So we have two signals and now we are ready to run. But before that we'll reduce the time of this simulation, and now let's run. So this is our simulation. So this yellow is the input supply and the blue one is the output of the full controlled rectifier. And now it is the time I'll tell you why I have kept the gate pulse of switch S1 and switch S4 same, whereas switch S3 and switch S2 are same. The reason behind this is, in positive half cycle the time would be from 0 to 0.01 second. In this duration, this terminal of supply is plus and this one is minus, and because of this the current flows in this direction, and the full path would be like this. So because of this, these are the two switches S1 and S4 which can control the output, and that is why the gate pulse of switch 1 and switch S4 are the same. Whereas in negative half cycle the time duration is from 0.01 to 0.02 or 180 to 360 degree. In this period this terminal is positive, this terminal is negative, and current flows through this direction. So in this period the switch S3 and switch S2 can control the output, and that is why the gate pulse of switch S3 and switch S4 are the same. Now the important thing is, now it's time to understand that why for switch S1 and switch S4 the equation is like this, and for switch S3 and switch S2 the equation is like this. The minor difference is of this additional 180 in switch S3 and switch S2. The reason behind this is, switch S1 and switch S4 are going to be triggered in between 0 to 180 degree. For example, if we are triggering the SCR1 and SCR4 at 40 degree, then we supposed to trigger SCR3 and SCR2 at 180 plus 40 degree. So in order to maintain the half wave symmetry, we supposed to trigger the SCR3, SCR2 at A plus 180 degree, and this is the reason why I have added this 180 degree in this equation. So it will help in maintain the half wave symmetry. But why we supposed to maintain the half wave symmetry? This half wave symmetry will help in to reduce the input side harmonics. If you are not too deep into this analysis of harmonics, then forget about this. But if you are really concerned about the harmonics, then this is really important. So I think it's clear to you that why it is like this. And now it's time to observe the waveform with RL load, and then you will be able to understand that what is the effect of inductance of load on the output of rectifier. See what's happening previously. When the load is just pure resistive load at exact 180 degree, switch S1 and switch S4 are turning off because the load is purely resistive. But now when the load is RL type, resistive plus inductive, so at exactly 180 degree, this switch tries to turn off, but because of this inductance, current suddenly cannot change its direction, and that is why the current flowing through both these devices is not reducing to zero, right? Current reduced to zero after several time, and once current reduces to zero, this devices gets turned off. So for this much of time, current flows in the same direction, but because the supply voltage changes its direction after 180 degree, the voltage applied on the load would be negative. But at the same time, current flowing through the load is still the same as previous in this direction. So this is what happens when RL type of load is connected with the rectifier.